Hi everyone, in this video we're going to learn about lines of best fit, sometimes called trend lines. So this starts off with knowing what a scatter plot is. And a scatter plot is something you should be familiar with, but just to review, a scatter plot is a graph in which two sets of data are plotted as ordered pairs in a coordinate plane. And what's important to know about a scatter plot is the two sets of data have to be numerical, which means that they both have to be related to numbers. So let's say that you kept track of every week throughout the year, week 1, week 2, week 3, and so forth, and how much money you had in your savings account, and then you recorded it. So we could take this numerical data and we could plot it on a graph. We would call our x-axis our weeks, and we would call our y-axis our money, and we would plot how much money we had. There may or may not be a correlation between the amount of money and the number of weeks we have our account. That correlation is also known as a relation. So what we're doing is we're actually looking at all of these points, the result of our experiment or survey or whatever it was, and we're trying to determine, is there a relation between these two words? That correlation or relation or even relationship can be represented with a positive correlation, no correlation, or a negative correlation. So for example, let's say that we were recording the number of weeks and how much money we had in our account, and all of our results started to show points that made almost a perfect straight line going from the bottom left up to the top right. We would call that a perfect positive correlation. Maybe the points aren't so lined up, but they still show somewhat of a pattern increasing from lower left to upper right. We would call that a strong positive correlation. Now, a positive correlation can also be weak. In other words, the points are a little bit more spread out, but we can still see that pattern going bottom left to upper right. Then again, maybe there's no correlation. Maybe we put money in our account and we spend it like crazy, and so there's no correlation. Or there could be a negative correlation, which means that the points are going from the top left down to the bottom right. A negative correlation does not mean it's bad. It just means that there is a downward slope. Remember when we graphed lines, any line that went in this direction had a negative slope. Any line that went in this direction had a positive slope. Well, the same happens for correlation. The points that tend to go from upper left to lower right have a negative correlation, or we could almost think of it as a negative slope. So negative correlations work just like positive correlations, where we could have weak, strong, or a perfect negative correlation. So let's just look at some examples here. The directions tell us to determine which graphs show a positive correlation, a negative correlation, or no correlation. And if there is a positive or negative correlation, describe its meaning in the situation. So look at the points here on this graph of the calories burned during exercise. The points are going from the bottom lower left up to the top right. Therefore, we would say that there is a positive correlation. So according to the directions, we then have to describe its meaning. So we could say that the, let me try to reword this. How about you burn more calories the longer you exercise. All right, let's look at number 2. So library fines, in amount of dollars and the books borrowed, the points are all over the place. So we would say no correlation. In number 3, we're weightlifting, repetitions, and the weight. So notice that the points are going top left to bottom right. So we would then say that there is a negative correlation, and then we can describe it. So what's going on here? Well, it looks like the amount of reps are going down as the weights are getting higher. So we could say that you do less repetitions the heavier the weights. Okay, number 4, car dealership revenue. So we have money in thousands of dollars on our y-axis, and then we have cars that are going from 1999 all the way up to 2008. So the cars are getting newer. Now this one is sort of tricky because the points are somewhat in a line, and there is only a very slight increase, but enough to say that there's a positive correlation. So then we could say revenue increases with newer cars. All right, so how does this apply to what we've been learning? So imagine taking all of these points and drawing a line through the points, okay? And that would be called a line of best fit or a trend line. So a line of best fit is a straight line that we draw through the center of a group of data points plotted on a scatter plot. It shows the general direction that a group of points seem to be heading. So let's look at this example here. Now I don't know what it represents, but I do know that these points have a negative correlation. Therefore, we could draw this line right here, this line of best fit, to show the flow or the direction of the points. Let's look at graph number 2. So we're talking about the height in meters of the women's high jump and the year that they were recorded. The points are increasing, so they have a positive correlation. And then this line of best fit was drawn through the points so that about half of the points are above and below, and it shows the direction of the points. That's the key word. The line of best fit has to show the direction of the points. Here's a line of best fit. Another one, and another one. I particularly like example number 6. Notice that this line of best fit that was drawn through the center of these points, showing the direction that the points are going, doesn't actually touch any of the points in the data set. It does not need to actually touch any of the points. And then here's one more. So maybe you know where this is headed. So with a line of best fit, what is the purpose? Well, the purpose is to make predictions. The first kind of prediction is called interpolation. And that's guessing data points that fall within the range of the data. For example, between the existing data points. The second kind, we'll talk about in a minute, is extrapolation. And that's guessing points beyond the range of the data set. So let's first start with interpolation. Let's look at some predictions. So someone recorded the average emails per day of people that are 0, 12, 24, 36, 48, 60, and 72 years old. And this was the result they got. So they drew a line of best fit through the points to show the direction that the points are going. There is definitely a negative correlation between the average emails per day and how old someone is. So we can use that line of best fit to make some predictions. So let's look at number 1. In graph example number 3, so this was from earlier. What is the average emails of a 40-year-old person? So let's see, we're counting by 12s. So halfway between 36 and 48 would be 42. So a 40-year-old person would be about here. So we would stop when we get to our line, and then we would go this way to our y-axis, and we would identify that number there. Well, here we're counting by fives. So 5, 10, 15. So maybe then we could say 17 or maybe 18 emails if we're off a little. Let's try another one. In graph number 6, so this is graph number 6 from earlier, what is the price for 900 units sold? So 900 units sold, this is in hundreds, so that would be right here. So I'm going to go up to my line, stop when I touch my line, and then bend and go over to the side here. So it looks like maybe $22 or $23. Without the line of best fit, without this line, I wouldn't know where to stop and bend to try to find my prediction. So now let's look at the second type, which is extrapolation. That's making predictions that we can't see on our graph. So for example, how many jackets will be sold if the snowfall is 82 inches? So here's my jackets, here's my snowfall, but there's no 82. 82 would be way down here somewhere. So in this case, I am going to have to write my y equals mx plus b linear equation. So I'm going to start by picking 2 perfect points. So let's use the points. Let me zero in on this. Let's use the point 35 and 180. And let's also use the point 15 and 120. So where was my other one? Okay, so I am very easily able to count my rise over run. So let's see, we're counting by 20s on the y-axis. So 20, 40, 60. Then it goes to the right, and on the right we're counting by 5s. So 5, 10, 15, 20. Simplify that fraction, so I know there's a slope of 3. Now I'm going to use my point slope formula, and I'm going to pick either point, it doesn't matter which one. So y minus 180 equals 3 times x minus 35. Do my distributing. And bring down my y minus 180. Add 180 to both sides. So y equals 3x plus 75. Now that I have a linear equation representing that line of best fit, I am able to make predictions that I can't see on the graph. So 82 represents snowfall, which represents my x-axis. So if I put an 82 right there for x, and I work out this equation, it will then predict for me how many jackets I can expect to sell if there are 82 inches of snowfall. This is how it ties in with what we've been learning. Let's look at another one. Predict the height in meters of the women's high jump in 2040. So it stops at 2020. So 2030, 2040. So I can't look at the graph to make that prediction. So I'm going to have to pick 2 points, make sure that they're perfect. So this time let's use 1930 and 1.6. And maybe we could use 1960 and 1.8. This one's going to be a little bit harder to do rise over run because they're counting by 0.1. They're counting by tenths. So let's just do the subtraction method. Let's just take y2 minus y1 over x2 minus x1. So that's going to give me 0.2 over 30. This is called a complex fraction. We learned that in 7th grade. So we can't leave a decimal inside our fraction. So using your calculator, you could take 0.2 divided by 30, or press your F to D key afterwards, and then your ABC key. But eventually, we're going to need to convert it to a fraction. There is a shortcut. I can multiply my numerator by 10, which moves my decimal to the end of the 0.2. But then I have to also multiply my denominator. So I'm doing this problem by hand without a calculator. So I end up getting m to be 150. All right, now I need to do my formula. Y minus y sub 1 equals m times x minus x sub 1. It does not matter which point we use. So let's just go ahead and use this one here. So y minus 1.6 equals 1 over 150 times x minus 1930. So y minus 1.6 equals 1 over 150x minus, give me a minute here to work this out, 1 over 150 times 1930 is 12 and 13/15. Then I'm going to add 1.6 to both sides. So y equals 1 over 150x. And let's see what I get. Looks like I end up getting negative 11 and 4/15. Okay, so there's my equation. So now I'm ready to throw in the point 2040. So let's take that and put 2040 in for my x. So y equals 1 over 150 times the year 2040 minus 11 and 4/15. And I end up getting y to be equal to 2 1/3 meters. Now let's see if that would be about right. So could I expect my high jump to eventually be 2 1/3? Sure, that seems very reasonable. Okay, we're almost done. Hang in there. So finally, you're going to need to know how to match a line of best fit with a set of data points. So you're going to have to be able to work backwards. So let's say that we have this scatter plot, and we know that one of these 4 equations is the line of best fit. So how should we go about this? Well, I'm going to just try each one of them. So I'm going to y equals mx plus b. I'm going to start at 0, and then my slope is rise 1, run 1, rise 1, run 1, rise 1, run 1. So you can tell by looking at this line that I'm making right here that it's going to be way too low. So we know that it cannot be number 1. Let's try number 2. I'm going to start at this number here, so I'm going to start at 1, go up 2 over 3, up 2 over 3, up 2 over 3, up 2 over 3. So that line is even lower, so that is below the points. So we know it's not going to be number 2. Let's try number 3. So I'm going to start at 4, go up 3 over 2, 1, 2, 3, over 2, 1, 2, 3, over 2. Well, that one's too high. So I am going to double check just to make sure that it's number 4. So I'm going to start at 1, go up 3 over 2, up 3 over 2, up 3 over 2, up 3 over 2, and that line goes directly through the points. So the answer is number 4. The last one is a little bit trickier. So what makes this one so difficult is right off the bat, when I look at my graph, this is not the origin. It is not 0, 0. So therefore, how would I know to start at 25? How would I know to start at negative 25? How would I know to start at negative 50? So what I find is the easiest thing to do when this happens is to draw my own. So here is my own line of best fit, right? So I just drew my own line of best fit. And I'm going to try to figure out my slope. And then I'm going to take my slope and I'm going to compare it to their slopes. So let's see. I'm going to take the point, let's do 600, comma, let's see, 100, 200, 300. Let's try 600 and 250. And let's also use 1,000, comma, oh, it's pretty close to being 500. Let's just use 500. So I'm going to do y2 minus y1 over x2 minus x1. So 500 minus 250 over 1,000 minus 600. So I'm going to get 250 over 400. And I'm going to reduce that to 5/8. So 5/8 is way far away from being 100. 5/8 is between 0 and 1 on a number line. 50 is too far away. Even 5 is too far away. So let's look at the fraction 1/2 and 5/8. Those are very, very close together. 4/8 would be 1/2. So look at how close I am. So I then can conclude that the answer is number 4.